Today I want to discuss the heap sort algorithm. We all know what sorting means, right? Putting things in order. For example, maybe when I look at an expense report, I want to know about the most expensive stuff. Sort by price. And I can see the new server is down here. On the other hand, maybe I care more about chronological order. So the question is, what's going on behind the scenes? How does the computer do this, and how does it do it efficiently? Remember, these could be much larger data sets, not limited to just a few things that I made up quickly on the fly. So this algorithm is called Heapsort. Let's take a closer look. Let's zoom in on this. So first of all, we get all these numbers as inputs, and they're all just in a simple list. This is the common way for a computer to handle data. Sometimes call this an array. It's just, this is what it natively knows how to do. It knows how to say, show me the third item. Initially, I have all these coded in red because, well, we don't know anything about them. They're probably wrong. It's just random. It came to us like this, and we don't know what it means. So the first thing I do, I say I'm going to consider this first part of the array, just this first number, as part of the heap. Nothing's actually changed inside the computer. We don't have a separate data structure over here. The data is still stored in one array, but we're just looking at it in a different way. And I've colored it yellow to say it's in process. This is stuff that we're working on. It says heap is good. Well, there's only one item in the heap, so there aren't that many ways we could arrange things. That's not a surprise. Okay, add index number 1 to the heap. We always start from 0. This is index 0, index 1, index 2. That's how computers work. So now, once again, all we're doing is we have just one number that says how many of these items are part of the heap and how many aren't. How many of them are in yellow versus how many are in red. Now we have a rule. The one above has to have a higher value than the one below. So the first thing we do, we just added this. We just, like I said, there was nothing to it. We just said, let's just put this at the very end because that's the natural place for it. But now we're going to compare. That's what this thick line means, that we're going to compare the two. And sure enough, the wrong one is on the bottom. We want 84 to be on the top because that's our rule. The larger number has to be above the smaller numbers. So we swap those two, and again they swap down here too. This is the exact same data, just a different way to look at it. And this is keeping track of how much work we've done. That's very important when you want to compare two sorting algorithms. Which one does less work? And that's how you know which one will be faster. Okay, now add index 2 to the heap. Same idea. And again, this is a tree. It's a binary tree. Each of these nodes is going to have 2 nodes underneath it. So again, we're comparing, just like last time. We want to know if this is right. And you know what? The bigger number is already on top, but let's go ahead and simulate that. And sure enough, it says heap is good. There's no more work to do. Last time we swapped 2 of them. Here, there's no need to swap. Okay, let's do another one. Well, remember what I said. Each of these is going to have 2 children. It's a little bit like a bracket for a sporting event, a tournament. The highest one, the one with the highest score, has to be on top above the ones below it. So anyway, this one goes in the next spot. And then we have to check. 74, yeah, it's greater than 39. So we want to, oh, I forgot to mention this thin line. This thin line here means that the 74 is also under the 84, so we should really check to make sure that both of those are right. This one is white because we don't even care about it. That's the beauty of this data structure. We don't have to compare every single item to every single item. So let's do the swap. And again, you notice that it's highlighted down here. This is where it's really stored, and it's highlighted up here. This is telling us how it looks. So let's do the swap. And now, just as I said, we're going to compare these two. Again, 74 is that new value, so we're not sure where it belongs until we do the comparison, and no surprise, we knew the answer, but the computer had to check. The heap is good. Now we can do the same thing with number 3. Excuse me, with index 4 has the value 3. So we're going to add it to the heap. Again, it's this very simple thing. We just keep going across, and when we run out of room, we'll go down to the next row. And once again, we're only looking at these two. At worst, we're going to compare this to these two items. We're not going to look at these other two. No problem. Compare 3 to 74. And we're already good. So again, we didn't even have to do that second comparison this time. That was a worst case. Okay, one more time. Let's put 41 into the mix. Now you notice something. Each of these, ever since we've been on the third row, we've had 2 of these lines change. So the cost, the worst cost, is that we're going to do 2 comparisons and 2 swaps. But the tree keeps growing. When we first got to this row, there was only 1, 2, 3, 4 items, and we looked at 2 of them. Then there were 5 items, and we looked at 2 of them. Now we have 6 items, and at worst, we're only going to look at 2 of them. So compare 41 to 2. And we've done the comparison, so we need to do the swap. We know that, remember the simple rule, the one on top needs to be larger than the ones below it. So let's do the swap. Boom. And now check if we need to keep going even higher. And we're done. We don't have to. It found its place. Again, that these 2 lines here, that was the worst case. Okay. Next one should be very similar. It's already telling us it's this 79, the double border. So let's try. Is 79 greater than 41? It is, so we're going to do the swap. Of course, this says what's Go going to do? What's the next thing that's about to happen? And then this is a slightly larger scale view, a macro view. It says that we are repairing things. We added something to the bottom, and now we're pushing it up as far as we need to go until we're done, until we're happy. So the next thing again is comparing 79 to 84. And 79 is less. It was already in the right spot. There's nothing else to do. Big smiley face. Again, the computer normally is doing this so fast. We're just slowing it down so we can see what's going on. Normally this would happen well, you saw it with the spreadsheet. It was faster than you could blink. All right, add item 7, the 25. Where do you think that's going to go? Next row. It had to. Each one of these rows is twice as big as the row above it. So we had 4 here, and 2, and 1, so this next row can handle 8. Each of these will have 2 children. There's 4 of them, that makes 8. Something else changed. It's possible that we might have to do 3 comparisons and 3 swaps. When we were on the 3rd row, we never had to do more than 2. Now that we're on the 4th row, we might have to do as many as 3. So let's do it. Compare 25 to 39. Nothing to do there. Again, that's just the worst case. 50. I think that'll be slightly more exciting. Again, 3 possible compares and swaps. Let's do the first compare, and it wants to swap it. It wants the 50 up here. Notice that we didn't have to compare the 50 to the 25. We already knew that the 50 was greater than the 39, and we knew from a previous attempt that the 39 was greater than the 25. So we didn't have to explicitly do that comparison. Again, this tree just keeps growing, but the amount of work, well, it also grows, but much more slowly. All right, 50 versus 74, heap is good. All right, let's try it again. 56, and swap it with the 3, but not the 74. That's good. Let's go again. In fact, let's just let it run on its own for a second. Again, we slow this down just enough for the animations to work. We don't, it's still isn't running anywhere near full speed. Okay, so what do we have here? This is the last one, as I said, 1, 2, 3, 4, 5, 6, 7, 8. And the possible cost is 3 comparisons and 3 swaps, and it looks like we're going to do all 3 this time. And then we're on to the 5th row. And you notice how we've used up most of these, more than half of these are already in the heap. So all that's left are these. And let's see. Go. And as I promised, this thing got longer. So it's 1, 2, 3, 4. So the possible cost is 4 swaps and 4 compares because we're on the 5th row. 1, 2, 3, 4, 5. So each time we add a new row, the cost is slightly higher for each item, but we have so many more items at that level, so these costs don't add up quickly. They get worse, but very slowly. All right. And that was an easy one again. That was the worst case cost. 16. All right, so here we grab the next one, same exact cost, 1, 2, 3, 4. So let's let this run for a second. What's going to happen once we fill the tree? Let's think about that. Well, the only thing we know for certain is that this is going to be the highest value. When we're done, we know the absolute highest value in this list will be right here. So any thoughts on what we might do? How about we move that back into the list? Here, we're almost to that point, so compare 83. Oh, wait, we just did the compare. Let's do the swap. So again, we just now put everything into the heap. These are all yellow. They're all in our working area. They're all in this upside down tree with the root at the top and the branches going downward. So where are we? We need to do this swap. And another compare. This one's going to fail. This one's going to say we're already in the right spot. All right, so now, not only do we have the heap is good, but everything's in the heap. So we know a lot about it. Again, like a sports bracket, like a tournament bracket. Each of these you compare, the ones on top did better than the ones on bottom. All right, now it says, move the largest value from the top of the tree to the end of the tree. Okay, so here's the top and here's the end. What do we know about the end? Well, it's also the last item in the array. So this value that's going to be the largest, we're about to put it right here to become the last value. So let's go ahead and do that. Let's swap those two. And notice how I changed it to green. They were red when I had no idea where they were going. They're yellow when they're in this working state where it's semi-organized, but still not quite finished. And this one is green, saying it never has to move again. Okay. Now the problem is we broke the heap. Remember the rule. The one on the bottom has to be lower than the one on top. And this one isn't, and it won't be because, I mean, we purposely grabbed it as the highest value in the tree, in the heap. So what can we do? Well, we'll just ignore it. Remember, we're not really moving the data. All we're doing is saying we have one item in this list and we have all but one in this list. It's just a single number that's just saying how many of them do we look at as a complete sorted list versus how many of them do we look at as a heap. All right, now the construction workers changed. Now we're fixing stuff down. Before we had a problem at the bottom and we pushed it up. Now we have a problem at the top. Remember, we swapped two items, so they were both wrong. This 56 was down here because it was less than 73, but now it's on top, so we need to promote one of these two. These two are the best candidates to be the highest value in the list. This is the winner of the AFC, this is the winner of the NFC. They're going to the Super Bowl to decide which one of them is the best. And that's what this line is. We're going to compare those two. Now we know that this is the best of these two. Now we're going to go ahead and do a second comparison, compare it to this top one. It's probably, I'm not even certain if this is ever needed. I should have looked this one up. In this case, it's certainly not needed, but I think in some cases we do need this extra check. So let's watch as it's running. Let's see. So again, we know that we have the best of these two. We're trying to find the best of these three to put at the top. So, do the compare. Again, it was a pretty good bet since we grabbed this guy from the bottom. It's a pretty good bet that he's going to have to move down again. But I'm not 100% sure. So let's just be safe and do that compare. And sure enough, it's in the wrong place, so let's move 95 up. Well, that's good. Once again, we know the largest value in the tree, but we're still not done. 56, remember, it's not just the largest one here, but every one of these has to be larger than its children. So we eventually are going to compare this to one of these two, but first we have to see which of these. First we're going to see which of these two is the biggest. And we compare and we decide 91 is the biggest. So it's the contender, and then we're going to compare it, and sure enough, it needs to get promoted in the list. So we swap those. Now, once again, we're working our way down, trying to push it down as far as it needs to go. And we need to see, same thing, we want, out of these three, we want the largest one to move to the top. So first we compare these two, which are the contenders. And 74, well, it beat the 25, but now we need to check it out against the 56. And sure enough, it is going to need the swap. Swap, so the largest value is on top. And go. Now what? Well, I can see it. We need the largest of these three values on top, and you can quickly see that it's already there. We don't need any more swaps. But of course, what did I do in my head in an instant? Well, the computer is going to show us slowly. The computer would do it even faster than you or me. But first we compare two of them. 50 was the largest. Then we compare that to the 56. And it's done. It didn't need to swap. It was already good enough. When we're at the top, it was more competitive. The higher you are, the more competitive it is. And when I throw someone new in at the top, he's going to have a lot of competition. This first one, he's probably always, I think he always has to lose. But as he goes further and further down, he's going to find smaller and smaller things and less competition. Okay, so once again, we have a good heap. And we don't have any more values to add. The red values are all gone. There's nothing else to add. So we know what to do. We need to move this 95, this biggest thing, into here. This is the spot that's reserved for the biggest item that we haven't settled on yet. The 99 isn't going to move. So we're fighting over second place. We know 95 is the best of everyone who's not green. So we're going to put him right here to be the best of everyone who's not green. So move the largest value from the top of the tree to the end of the tree. And again, I marked it as green. That one is never going to change again. He is definitely in the right spot. So we know what to do. 95 is greater than 73. We know that for certain because we purposely move this down from the largest spot. It's always going to be wrong, but we know it's really easy to deal with. Again, just changing one number. Instead of saying we had one item that's complete, we now say we have two items that's complete. That's all that happened when I did that. The animation was just to remind you that this and this are the same. Okay, now remember we swapped two items. We just took care of one of them. Now we have the 66. Again, this was on the bottom. It was a small number. We're fighting with the big dogs now. 91 is on top. It's a big one, and so is 84. And, well, let's do the compare. And let's do the compare, and again, swap. No surprise, just like last time. All right, let's take another look. We have 66 versus 74 and 83. Well, let's do the two contenders first. This guy's already got the spot. And instead of him fighting every contender, we'll have the contenders fight with themselves first. Sure enough, 83 won against 74, so now he earned the right to duke it out with the champ. And he won, so let's swap them. Then we keep pushing down. So how much is this going to cost? Remember, on the way up, we said worst case, you're just going to go every line between you and the top. That could be a compare and a swap. So what's happening on the way down? Well, it's similar. We're limited by the height of the tree. We're not comparing you with every single item. We're never going to look at the rest of these. 84 had its chance, but it didn't make it, so no one under it is going to make it. Same thing over here. The 74. It had it already lost to 83. 83 is up here. So there's just no need. The only thing we need to do is work our way down the tree. So worst case, it's the height of the tree. 1, 2, 3, 4 in this case, because it's, well, there's 5 levels and 4 edges. And then for each one of those, we could do at most 2 comparisons. So remember, we do first the contenders and then against the higher one. So it's the number, it's the height. Again, this is the cost for each item. It's the height of the tree, that many swaps, and twice that many compares. Okay, so it has that same nice property where as we keep adding more and more items, it's not really, it's not going to get much worse. We're still going to have to look at every item, but the amount of work we have to do for every item, and it does increase every time, but it doesn't increase by that much, and that's the important thing. This little case here where I punched in a small number where I could fit them all on the screen, this doesn't even matter. once you get to more and more items, the curve is going to look better. I'm going to show you some curves in a minute. And basically, this thing is just noise, this small thing. It's just to show you what we're doing. But these costs, the important thing is how do they grow? And it's the same thing over and over, a little bit relaxing. Oops, we just reduced the height of our tree. So that means that the worst case is just reduced. So we're going to 1, 2, 3. So at most, there's 3 swaps that are possible and 6 compares. Where before it was 4 swaps and 8 compares. So this one did go all the way to the bottom. Sometimes you do. And we're really talking about the worst case here. We're talking about someone could order the data specifically in a way to make your job hard, or just bad luck, Murphy's Law. The other thing, we talk about the cost of an item, and I said it depends. When the tree was down here, it was higher than when the tree gets shorter and shorter. Well, it turns out that you don't have to worry about it that much. So you notice each level is bigger than the ones much bigger, well, twice as big as the ones above it. And in fact, each level contains more items than the entire other tree above it, the entire rest of the tree. So in a minute, I'm going to show you, it's already up here, I Googled it, I didn't have to draw these curves myself. But it's going to show you this cost, and really the simple way to estimate it, we say what's the cost for these on the bottom, because remember that's the worst and it's the most common case, and then you multiply that by the number of items in the list. Fairly standard way to estimate things in computer programming. Whoops, now we're shorter again. We only have 2 possible swaps. But again, there's so few of these that you don't even consider, and this is just moving faster and faster because of that. Almost done. So now what? We have 2 left. We have to repair the heap, but it's so easy now. There's only 2 items. There's only 1 swap to do. Again, there's no reason to discuss that in my estimate. I'm not going to say -1 swap because in the worst case, this one's just never going to compare, one compare, because there's nothing else to compare this to. It's just not worth it. So let's go. It's already right, so we're good. So we're now going to move this down, just like we've done so many times before. And again, it's green, so now we only have 1 left, and we just need to update our picture here, that's all. And then this one, there was nothing to compare to. There's no edges, so it's right automatically. So again, all we do, we already colored it green. We just have to stop pretending it's up in this tree. This tree is totally imaginary versus this. This is real memory that's all allocated in one big block, exactly like it looks on the screen. Beautiful, we're done. Now we can try again. Let's see, let's start with, you know what? I made this big, but you can't hold as many things. So let's look for twice as much now. Remember, this will be more than twice as much work, but not terribly more. And you know the basic idea, there's just going to be more of the same. In fact, while that's running, let's take a look at this picture. So, whoop. There we are. So, this is somebody comparing, well, we have in here. You know the amount of the number of items that are in the list. That's n. Unfortunately, the amount of work we have to do a certain amount of work for each item, but it's not a fixed amount of work. We have to do the height of the tree times the number of items. And that's, if you don't remember math class, that's what a logarithm is. It's how high is a tree with that many items. So n, the number of items, times log n, the amount of work per item, that's this purple line. So you see it is growing faster. If I have a tree that's twice as big, like we just did, it's going to take more than twice as the amount of time. N squared. Well, why did we go through this complicated thing with the tree? Surely if I asked you to sort this, you never would have come up with this algorithm. There's a lot of ways, and I'm not going to list them all right now, but there's a lot of more obvious ways. Like just go through the list and find the largest. Don't worry. That's all we were doing here. What if we didn't keep this tree? We just looked through the list to find the largest item, and we immediately grabbed it and moved it to the end. And then we would save a bit of work because we only walked through the list one at a time. Well, then we'd go through a second time, but we wouldn't be able to reuse this work. And basically, the cost would be n times n because you're comparing every item to every other item pretty much. Really half that, but again, for the sake of our estimate, the half doesn't show up. And the important thing to notice here is not just that this value is taller. You could always write a slightly faster algorithm to make that shorter, or, optimize something, or, there are certain places where I said I knew we wouldn't have to compare, but I did it anyway. We could get a faster computer. You could make that go down a little, but the problem is this thing is curving the wrong direction. So here we have 10 items. Now we have 100. Well, we can see n log n is grown compared to n, so that's what I was saying. Having 10 times as much will take more than 10 times as long. But it's nothing compared to this naive approach to sorting, the thing where we're not reusing our work and saving this intermediate state. I mean, think about it. Every time I wanted the new highest number, all I had to do was grab one of these two. And then a little more cleanup, but I didn't have to look at every single item. Okay, and you notice this is going off the chart. It can't even show you what the naive thing would take. And then here it is with 1,000. This is what I was saying. We have such a small example here. We had 45 right now, so half of this. So right just before we got cut off. And then again, it's only going to get worse as you have a big list. Is 1,000 even a lot? What if you're trying to sort a phone book? How many names are in your city? How many phone numbers are in your city? So this, again, is why we're winning. Okay, so let's check in with our construction worker. Making some good progress. Oh, we're already on the way down. I didn't even notice that. So more than halfway through. 84 and 0 is 2. Yeah, well, 0, you knew 0 was going to lose. So is Heapsort the best? Well, it's certainly better than the naive one I was describing. There's some other options. I think I'm going to do a binary tree selection sort. It looks similar to this, but it's easier. You have to use more memory, but in exchange for that, you don't have to do as much cleanup every time. All right, well, I'm just going to let this run for a while. I think that's all I have to say on the subject. It is... Now, there are reasons why this curve, this n log n, is the best we can get. But again, you might be able to get just a slightly, maybe twice as good or something. It won't show up the same way on this chart. But we're certainly in the ballpark. We have certainly destroyed. It's one of the first things you learn when you get to serious programming. You can write something that's technically correct, but would just take forever to run. So it's not really a good solution. All right, well, enjoy the show. Almost done. Just keeps getting faster and faster. Man, that 0 just keeps getting moved around. Done.